Okay, so we are actually doing radiation, and so basically we all know that accelerated charges radiate, and radiation means that the magnetic and electric field uh, varies like 1 over r at large distances, which is different from electrostatic or velocity fields, which go like 1 over r squared. So the fields fall slowly compared to uh, the case when you don't have acceleration. So that's why accelerated charges can radiate and carry energy to far distances. So the reason we can see light from objects like stars which are so far away is because of this retardation effect, right? This retardation effect causes, I mean, it's related to the fact that there is a finite time that light takes to travel, and that causes a term in the uh, in the potential and the fields which varies as 1 over r. So it's actually very, very important and fundamental. Okay, so last time I was actually trying to show something here. You can see my screen?
Yes, sir.
Yes, sir.
Okay, good. So I had not drawn the figure quite nicely, but here is a figure that I took from the internet. And what it shows is, so you have a charge which is moving at 0.8 C, for example, along the x direction. Okay, so after some time, it is at this point, and the light which left, it is sort of moving with a constant velocity, let's say, along the x direction. So the charge reaches here, and we know from the velocity electric field that the field lines point to the instantaneous location of the charge at the time when you're measuring the field, not at the retarded potential. So if the charge were here, then the field lines will actually be connecting radially to this point. Okay, so this is the field lines. This is the direction of field lines. Now, instead of moving at a constant velocity along the x direction, if it is stopped at some time here, so it would have been here, it hadn't stopped. So it got retarded, it experienced acceleration for a very short time, delta t. Say delta t is the time over which this stops. Its velocity goes from a 0.8 c to 0 over this time scale delta t. Okay. Now, the fields at large distances, like observers at large distances, this information that the charge has stopped hasn't still propagated, because the light travel time is given by this circle. This is the only volume within which this information that the charge has stopped has propagated. So outside world thinks that the charge is still moving at a constant velocity. So outside this radius of causal contact, the electric field should point to the position of the particle had it not stopped. Okay, but inside this causal contact, right, this charge is now at rest after time delta t. So delta t is much smaller than the time that the charge takes from going from here to here. It's like small time. Right, so what happens is within this radius, right, within this the charge is at rest, and you have radial, almost like electrostatic field lines, right? So for example, a typical field line would look like this. Okay, so you can actually see just this from this diagram. The only way you can connect a field line across this time delta t when the charge accelerated is through this tangential component, right? We know in vacuum electric fields cannot end abruptly, they have to continue, because del dot E is equal to 0, right? So this is the only way you can connect it, and you can actually just see diagrammatically that the density of field lines is much higher here at the location where the pulse has traveled from here till here, right? At the causal radius. Okay, and this is also in the tangential direction, right? If you recall your formula, this formula, radiation formula, that the electric field is along n hat cross n hat minus beta cross beta dot. So beta dot is in the x direction, right? Because the charge stopped. So it is in the minus x hat direction. Beta dot is minus x hat direction. N hat minus beta depends on which line you're observing. So right here n hat minus beta is along the x hat direction. Right. So how do you know that this electric field here goes as 1 over r instead of 1 over r square? So so these are the field lines which are drawn. So E, the electric field strength, is equal to number of field lines divided by the area, right? This is the definition of field strength, right? If you consider field lines, the number of field lines divided by the area. So here the field lines are stronger compared to here because the density of field lines is higher. Now, if we consider this portion before the discontinuity or after the discontinuity, area goes like r square delta theta, where this angle is delta theta. Okay, so electric field, which is radial, goes like 1 over r square, the standard velocity field or electrostatic field. Now in this portion, in the tangential portion where the magnetic fields are tangential and dense, there the area goes like r delta theta, right? And the width of this is c times delta t, right? This time scale for acceleration. So you see, so I mean the same. So 1, 2, 3, 4 field lines, right? 1, 2, 3, 4 field lines will go through 1, 2, 3, 4. These, they will continue 1, 2, 3, 4. They are continuing here, right? So the number of field lines is the same. We are considering area such that number of field lines is the same, but the area is much smaller. It is only proportional to 1 by r instead of 1 by r square, because the transverse direction has a width which is c delta t, and that's independent of r, right? C delta t is the same. If you look at the same situation after some time, this this circle would move here, right? But the width will remain the same. It's c delta t. Whereas as you go to larger radii, the area will fall off like r square. So that's why this is one way of seeing that the electric field is tangential and falls off slowly, like in radiation. And you can actually also see that the direction given by this formula. So if you are looking here in the transverse direction, so if you're here, like for example, this is where the n hat is in this direction, n hat minus beta is sort of in right. So I mean, the general case is somewhat harder because this n hat minus beta makes it a little difficult. But if your beta is, say, small, say the speed of the particle is not 0.c but say 0.01 c or 0.1 c, in that case it's just n hat cross beta dot, right? It is basically let me just draw. So for beta much less than 1, right, n hat. And recall that this whole thing is calculated at the retarded time, right, at a time which is somewhat earlier than the present time. So n hat cross beta dot, and beta dot is this acceleration term, right? So this is equal to, from the vector identity, this is n hat dot beta dot in the direction of n hat minus n hat dot n hat, which is 1 So basically this is equal to minus beta dot perpendicular, right? So this minus beta dot perp is the component of acceleration. So this is component of acceleration. Of course, for acceleration there has to be a c here, perpendicular to n hat, right? I mean, this part is nothing but beta dot parallel n hat, right? This is the component of beta dot along the direction n hat. So this is nothing but beta dot n hat. So beta dot minus beta dot n hat is nothing but beta dot perp, right? So basically, if this is the direction beta, this is some direction n hat, right? So this right, so this portion is beta parallel n hat, this vector, right? And then this is beta perp n hat, right? So this is what I'm sorry, let's say this is beta dot is what we're talking about. So this is the acceleration direction. So in case where the particle velocity is much less than c, what matters is, the electric field is in the direction of the acceleration, the component of acceleration perpendicular to the line of sight. So this is nothing but line of sight, right? The line connecting the observer and the source, evaluated at the retarded time. Okay, so if you're here, right, so particle has stopped. So this guy, at the retarded time, this guy should be here, right? So this is the direction and this point and this point. So, I mean, this is just, yeah, from the last time. Any questions here? No? Are there people in the audience? Yes.
Sir, can you repeat that, in the figure what you have shown? I'm not able to get it.
What is it that, who is asking the question first? Can you
sir, I'm Sachin.
Yeah, so what is it that you...
Sir, means how means you just solve the cross product and then you got the terms like means you got term by means the first one, this is n dot beta dot n cap minus b dot perpend, and you are calling this as perpendicular.
No, this, right? Beta dot parallel is the component along n hat, right?
Okay.
This is the parallel component. This is the total vector, right? So the total vector, so A, for example, some vector A, we can write it as A parallel n hat, some unit vector n hat plus A perp, right? We can write any, if we have two vectors n hat and A, we can write A as a component along n hat and a component which is perpendicular to n hat, right? And A parallel is nothing but n hat dot A, right? You can actually do a dot product of n hat of this. N hat dot A perp will give you 0 because A perp is the vector perpendicular to n hat, right? So this is A parallel, so A is equal to A parallel n hat plus A perp. And so basically what it means is A perp is A minus A parallel n hat, right? So this is like a general thing that is pretty commonly done. If you're given some vector, you can write some other vector as a vector which is parallel to that and perpendicular to that. This is it somewhat clearer?
Yeah, sir. Now this is just subtraction. Okay.
Yes, it's just, this is a general method in which you can write a vector in terms of some other unit vector. Okay, but the interpretation is actually quite nice, that in the non-relativistic regime, the electric field, which is this, right, this is n hat, this whole thing actually is in the direction perpendicular to n hat. It is along the acceleration component which is perpendicular to n hat. So this will be useful later. Any other question? Okay, then let's move to the next part. Okay. Yes. Okay. So what about the spectrum? Right. So we talked. We wrote this expression for E as a function of R and T. Right. So, but we also are interested in how does E, I mean, there is this Fourier representation in which you can also write E as a function of R and omega, right? Or sometimes you write it as E omega R. So they are equivalent because if you take a Fourier transform, you talk in the Fourier space. So we want to go to the Fourier space so that we can actually tell you about how the power is distributed at different frequencies, for example. Okay. Now, so let's go back. So in one of the previous classes, we showed that when we were dealing with these concepts, we showed that dW, dA, d omega is equal to. So basically, this is the energy of electromagnetic waves which are crossing some area dA per unit frequency d omega is given by C E at omega square. This is just from the Fourier time. And what we also should recall is that is given by 1 by 2 pi E T. So I'm actually suppressing R here, but E is a function of both R and time. Right, so this is what E hat omega, the Fourier component of E is given by. This is also a vector. Just like this, there are 3 components of this. Okay. Okay, so okay, let's see this one. We also know, so if you have some area, so there is some source which is emitting radiation, and this is the area, right? We know that dA is equal to d omega times r squared. So if this is the distance r, and we know this dA, the area where you're measuring the electromagnetic energy crossing, that's just, and this is d omega solid angle, this is equal to this. So we can actually write dA as so dW by d omega d omega. So energy crossing per unit solid angle is nothing but C r square E hat omega the whole square. Okay, and we have to actually use this. So there are some steps involved, but let me actually write this down. First, let me write this down for pi square integral of R E T. Right, so this times e to the I omega t dt. right? So this is just, I mean, what I've done is just taken this R inside, and what I'm actually going to do is I'm going to use the expression for ET from our radiation expression that we had previously, right? If you recall, this is actually given by n hat cross n hat minus beta cross beta dot times kappa to the minus 3. If you recall, what was kappa? Does anyone know what kappa was? We actually defined a kappa. This is a very, very important factor.
1 minus n beta.
1 minus n hat
Beta.
beta, right? So basically, this is like a component of beta along the line of sight. So if you have a charge which is moving towards the line of sight, then this can actually be very kappa can actually be kappa goes to 0 as n hat dot beta goes to 1, which of course never quite happens for massive particles. But what this reflects is the effect that, right, if you have a charge which is moving very close to speed of light, right, all there is all this radiation that it emits along its motion reaches the observer in a much shorter time. So delta T emission is much bigger than delta T observed, right? Suppose this was moving at C, for example, right? So if it is moving along the line of sight at C, all this radiation which is emitted will actually reach the observer at 0, within, at the same time, because this guy emitted something earlier, but it also travels longer path. This is later, but it travels smaller path. So all these radiation which is emitted on the path reaches the observer at the same time. So that's why delta T observed can be tiny. So this can have very important effects. Okay, if the particles are moving relativistically. Okay. Okay, so this is this, and right, so there was this 1 over R factor. So this is just the radiation field, and we have to calculate this at the retarded time, right? So this is this square bracket here. Okay, so what does this become? And there's of course Q here, right? The charge. So this thing becomes Q squared by 4 pi squared C. So let me, yeah, so there is actually also a factor of C. So in the end we have C by 4 pi square here. And so there is a C squared at the bottom, I think. So that's why you have 1 by C. And then you have this integral e to the I omega t dt, and this becomes squared. Okay. Right, so we know that T prime is equal to T minus R T prime by C. You recall the geometry that you have some charges here which are emitting, and you are looking far away at this point. So this is your R, okay, and yeah, so R is nothing but C T minus T prime. So basically you're calculating using the condition of your charges and current at an earlier time, which corresponds to this. And this is also equal to R minus R naught T prime. So this is an implicit relation for T prime. And from our previous considerations, we actually know that kappa dt prime is equal to dt. This is the change of variables that we did previously, and this actually, is somewhat related to what I just said there, that dt, the time for the observer, can actually be much shorter than the time in the emission for the particle which is emitting, because of this light chasing light effect. This is called a light chasing light. Right, so this can actually give you a dt which is very small compared to dt prime, the retarded time interval. Okay. Right, and the other thing is, if the charges are, if the extent of your charges which are emitting, L, is much less than R, the distance at which you're measuring. This is always the case for astrophysical measurements, right? The sun, for example, the charges in the sun are very close compared to the distance between us and the sun, and then much more for farther away objects. So in this case, what we can actually do is n hat. So this is your n hat direction, right? What we can actually do is r t prime is equal to, right? We are actually doing this. So r minus r naught t prime dot r minus r naught t prime, right? We are just taking this square root, and let's sort of consider our coordinate system somewhere, and so this is equal to r squared minus twice r dot r naught plus r naught squared, square root of that, right? And we are assuming that r naught, r naught is much less than r, right? So the observer is very far away. So in that case, this is actually quite small. So we can actually do a binomial expansion. We can do a binomial expansion. This becomes r minus n hat dot r naught, right? So so basically, what I've done is I've ignored this term, and I have done, brought the r square out, and then just did a binomial expansion, and I'm actually assuming that r hat is equal to n hat, right? And that's a good assumption, because this distribution of charges is much more compact. So even if you go to extreme, n hat is almost the same, right, as r hat, small r hat. So the direction of the observer is almost the same throughout the charge distribution. So this is a good approximation. Okay, good. So what this will do is, now we'll do a change of variable from t to t prime. Okay, so let's see. So 1 by kappa dt, 1 by kappa dt is dt prime. So this kappa to the minus 3 becomes kappa to the minus 2. So let me just write down. So dw by t omega d omega is equal to q squared by 4 pi c integral of n hat cross n hat minus beta cross beta dot kappa to the minus 2. Okay, let me just put this bracket, kappa to the minus 2 e to the I omega. So now t is t prime minus, so t is and I said that this r and the location of the observer are almost the same. So So this is okay, so e to the I omega t. T is t prime plus r. And dt becomes dt prime. That kappa factor goes away, and then you have a whole square of this. Okay, and here, if you look at this expression, we have actually simplified. So you see, RT prime is a little inconvenient because it's different for all, location of every point. But R is fixed. R is just the distance, from some coordinate system. It's good to choose the coordinate system, say at the center of charge, If we choose it at the center of charge, the origin of the coordinate system, things become much easier. Center of charge meaning summation, so dipole, so summation qi xi is equal to 0. We can actually choose a coordinate system, which is basically within, this is actually not even necessary. We choose a coordinate system which is within the body, which is emitting. Okay. Oops. I'll have to redraw that. Let me redraw it. Okay. So this, if I take it as r minus n hat dot r naught. Of course, this is a function of t prime by c. Right. So if you have e to the I omega by c r, this is an integral over t prime, so this will just come out, and if you take an absolute value square, that just becomes 1. Okay, so what you have is, I will actually simplify this guy. So this becomes e to the I omega t prime minus n hat dot r naught t prime by c. Okay. Now, what you can actually show is that if lambda by r naught, if much less than 1, right, that is the wavelength of the light, not r naught, sorry, lambda by r, this observing point, sorry. Basically you are far away, you're in the far away zone.
Sir.
Yes.
Sir, how have you gone from dt to dt prime, sir? Means
This is
t
just a change of variable that we are doing.
Sir, but t depends on rt prime. It should be there. Means
t depends on.
Sir, rt prime means it's there now. Means,
no, just a sec. Right, so t is actually fixed. Right, so if you're observing something at time t which is fixed, it's t prime which is different from every different particle. Right. So there is a 1-to-1 mapping between capital R and t prime.
Okay, sir.
Right, so once we have a fixed t, then we have that relation, and then we just sort of do a change of variables. In fact, yeah, I think this is the assumption. So if we make this assumption, then it turns out that you can actually show that dt prime n hat cross n hat cross beta by kappa is equal to n hat cross n hat minus beta cross beta dot by kappa square. So I'm actually not going to show it. I have a homework problem where you are asked to show this. In fact, let me see if I have that all open here. Yes, here. Show that this is equal to that, where this is this, assuming that lambda by r is much less than 1. Recall that this identity is used to simplify the expression for the frequency and angular distribution of power. So this is not R naught, actually. Lambda is much less than R. That's the assumption. Not R naught. Okay. So good. So this is, so if we make this, then you can actually, what you can actually do is, you can do an integration by parts. Just let me make it big screen. So you can do an integration by parts, right? Because this is d dt prime of this thing. And then you have this function is very easy to, right? So you have to integrate this part and then differentiate this part. This is very easy to differentiate. So, and if you sort of make certain assumptions in making that integration by parts, then, and you know, the certain assumption, right? You know, basically what you will have is integral d dt prime n hat cross beta by kappa. So this is what your thing will become. So this is this whole thing, e to the I omega t prime minus n hat dot r naught t prime by c dt prime. So this is the integration that you will have, right? If you integrate it by parts, you have this first part n hat cross beta by kappa e to the I omega, this whole thing, right? And this is, you know, you sort of put the limits from initial to some final condition. And what you assume is that you have a charge or a charge distribution which has, and in fact, we're actually considering a single charge here. So if your beta at an initial point and a final point were 0, then this boundary term will give you 0. And then you have minus n hat cross beta by kappa and then you take a ddt. I mean, you have to do a derivative of this one, so you get iota omega so 1 minus n hat by c dot d by dt prime r naught t prime right, and then you have e to the I omega t prime minus, you know, the whole thing dt prime. So you will have this integral. So oops, just a second. Right, so we also know this dr naught dt prime. Right, so if you recall, this is nothing but kappa. So this kappa and this kappa will go away, and in the end, this dw, I mean, this is somewhat tedious, but not difficult to do. This becomes equal to q squared right? So there is this iota omega in this integral, so you're taking a squared of that, so that will become q squared omega squared by 4 pi square c, and then you have this n hat cross n hat cross beta dot exp iota omega t prime minus n hat dot r naught right. So this is the expression, the final expression. So it's somewhat easier than this kappa square expression, and this kappa cancels this omega square. So basically the power is actually proportional to omega squared. So this is the power per unit frequency. So at a given frequency omega, this goes like omega squared. Okay, so now we'll go to more simplification. We will go to right. So if you have non-relativistic particles, if you have non-relativistic charges. So radiation due to non-relativistic charges. What happens in that case? I mean, basically beta is much less than 1. In that case, n hat minus beta just becomes n hat. So your expression n hat cross for electric field n hat minus beta, I mean, I already did this, so cross beta dot, this just becomes is equal to minus beta dot perp, right? I just did this previously, so I'll not do it again. Okay. So if we actually calculate the magnitude, so in the non-relativistic regime, if we calculate the magnitude of electric field in the radiation term and the velocity term, what do we get? We get so beta is much less than 1, so it is just recall the radiation goes like 1 over r, this goes like 1 over r square, so there is a r in the numerator here, and there is a u dot, the acceleration, divided by c square. So if you look at the expression, this is what you will actually get. So that just the order of magnitude value of the radiation, the velocity terms is given by this, right? And I mean, if it is like an oscillating charge, for example, we know that u dot is nothing but, if it is an oscillating charge, u dot is nothing but frequency times u itself, right? Like an oscillating dipole, right? So if we assume that, then what we get is this, we can write as r by c squared. This is dimensionally correct too, right? Good. Nu times u. And c by nu is lambda, so r by lambda times u by c. Right, so u is some like velocity of an oscillating dipole, for example, right? And u is much less than c. So this is small. We have assumed that this is the, so this is sort of let's say this is the wavelength of the emitted light, and r is the distance from the observer, right? So r by lambda can actually be very, very big, right? You know, typically this is very, very big. And this is small, but this is actually very, very, very big. So, I mean, we also define something called a near zone and far zone. So near zone is r much less than equal to lambda, right? And in the near zone, if r is smaller than lambda, u is much less than c, the velocity field, right, in the near zone, E well is bigger than E rad, because u is much less than c. And the far zone is where r is much bigger than lambda c by u, right? So so basically this is much bigger than 1 in the far zone. So we get this E rad is much bigger than E well. But you can have an intermediate between these two where the two electric fields are comparable, right? Because this is much less than 1, this is much greater, much greater than 1. But at some r, they can sort of be comparable, right? So that is the transition from near to far zone. Okay, is this clear? So this is sort of like the transition. Yes. And this is far zone. You know, this is where it really becomes like a true radiation of the kind that we are familiar with. Here it will have very similar behavior as, you know, like you know, not really statics, but electrostatics like, in the sense that field goes like 1 over r square. So that's why it's velocity field. Okay, so this is fine. And then let's go to Larmor formula. So Larmor formula is the power radiated for power radiated by a non-relativistic accelerated charge. Okay, so we have to get this. So let's see. So we have E rad is equal to Q by R C squared n hat cross n hat cross U dot. Okay, so this is the expression. This is just this, right? And this is nothing but minus U perp dot, right? So this is the electric field in the radiation zone here in the far zone, basically, right? Due to a non-relativistic particle of charge Q undergoing acceleration U dot. Okay, so let's look at how this looks like. So let's consider a charge here, and let's consider some general direction n hat, the line of sight where the observer is located, and let this direction be the direction of U dot. Right, this is the retarded time. At the retarded time, this is the direction in which the particle is being accelerated. Right, and as I said, so this, you know, if this is U dot, you know, this is, right, so this is the perpendicular. So this is U dot perp, right? And this is minus u dot perp. So what this is saying is that the electric field is along, is basically q by r c squared u perp dot, right? And as I said, this is u perp, this dotted line is u perp, so it's minus, this is there's a minus sign here because of this. So this is the direction of the electric field at the observer, and let's just call this angle theta. This is the angle between the acceleration and in the direction n hat. And recall, this is actually evaluated at the retarded time. So at the observed time, this particle will not be here. This particle may be somewhere else. But this is the location at the time when left the source and the radiation which is observed now. Okay. Nice. So in all these formula, it's always the retarded time. We have to be careful about this because the light takes finite time to travel. Okay, so this is the electric field. This is the expression. Okay, and what about the direction? So the direction of electric field is E rad in this case lies in the plane of n hat and u dot, right? And in fact, it's along u perp dot, which is in the plane of n hat and u dot. Okay, so this is the electric field, this is the n hat. What about the magnetic field, B rad? We know that this is nothing but n hat cross E rad. Of course, this is also evaluated at the retarded time. Okay, so that would be n hat cross, right? So this is u. So this is n hat. So this is into the board, right? So this is the B. This is into the plane. This is B rad. Okay. So now let's see. So so this is the expression for electric and magnetic fields in the far zone due to a charge which is accelerating, a non-relativistic accelerating charge. So the electric field is perpendicular to n hat, and in fact it's proportional to minus u perp dot. Okay, so so basically B rad, the magnitude is actually equal to E rad, because n hat, B hat, and this is a triad. So if you take n hat and E hat are perpendicular, so the magnitude of B will be the same as magnitude of E. This is what was true for our electromagnetic fields. And what does this also mean? This means that the radiation is fully polarized, linearly polarized. Right? Because it's sort of oscillating in this plane with this amplitude. Okay, so we can actually calculate this. The absolute value of this would be Q U dot. Let's just take the absolute value. So this is just the acceleration, and perp will be just U dot sine theta, right? Sine theta. That's U perp. Absolute value of that by RC square. So this is your the magnitude of your field is just this Q times acceleration sine theta by RC square. So now when theta is 0, for example, let's consider these special cases. So if the charge is accelerating in this direction, and if you are looking from here, right? So the acceleration is along the line of sight. So U perp dot is actually 0. So you see E equal to 0, right, in this direction. If you're observing here at 90 degrees, acceleration, the perpendicular component of acceleration is maximal. So you have E maximum. So So you know your amplitude of the field goes like sine theta, where theta is this direction. So you don't receive anything along the direction of acceleration, and you are maximally you receive maximum right perpendicular to the direction of acceleration. Okay, good. So this is nice. What about the flux, right? If we recall our Poynting flux, S, right? S was C by 4 pi times E cross B. So, you know, E and B are perpendicular. We have already argued about that. And n hat is perpendicular. So E cross B, so E cross B is actually n hat. So this is nothing but, you know, so basically this implies that S, the magnitude, is equal to C by 4 pi. E and B have the same magnitude, E squared, and this is along n hat, right? This is also very clear. N, E, B form a triad for this particular case. So this is that. So this is equal to C by 4 pi Q square U dot square sine square theta by R squared C4. So this is just C cube. So this is your Poynting flux. This is the power crossing radius R per unit area per unit time. So this is, what is that? So this is nothing but, you know, the actually dW by dt d omega. This is the energy crossing. Sorry, not this. Just let me be a little more clear. Right. So this is S. What about energy crossing per unit area per unit solid angle? Right. So that's nothing. So 4 pi R square is nothing but you know, this is just a sec. So so this is equal to R square S basically. And when I write S like this, it really means absolute value of S. This is equal to Q squared U dot square. Again, U dot is like absolute value of U dot square sine square theta by 4 pi C cube. Okay, this R square goes away. So this is just the power crossing particular angle theta. And as I said, when theta is 0, you get 0 in that direction, no power. Here it's maximal. Okay. So what about the total power? This is the power along a particular angle theta. So the total power d omega dt, energy radiated per unit time, is equal to d omega dt, d omega, you know, integrated over the whole solid angle. So this is equal to q squared u dot squared by 4 pi c cube. That's that, and sine squared theta. So this is this, and d omega is, what is d omega in terms of angle theta? Sine theta d theta d phi, right? And you know, it's pi symmetric, so this integral of d phi just gives you 2 pi, and this is what you have to do. This is nothing but, so 2 pi and 4 pi, so it's q squared u dot squared by 2 c cube integral sine square theta sine theta d theta That's nothing but 1 minus mu squared d mu, where mu is equal to cos theta. This is a change of variable. -1 to 1, but you can go 0 to 1 and multiply it by a factor of 2, so that 2 and this 2 cancel. So you have this is nothing but q square u dot square by c cube, and you'll have 2/3. This is the famous Larmor formula. This is Larmor formula for power radiated by a non-relativistic charge which is accelerating. Okay, e square a square by c cube, 2/3 e square a square by c cube. This is nothing but acceleration. Okay, so this is Larmor formula. Is this clear?
Yes, sir.
Okay, good. So this simplest case is the most, we use this most of the times, but relativistic effects are also very, very important in some objects, like, compact objects, pulsars, and, jets around black holes. But in most of the cases, we can get away with simple non-relativistic formulae. Okay. So we can actually, so this was just for a single particle, but we can actually consider a collection of non-relativistic particles. So collection of non-relativistic particles. So what do we do in this case? So consider you have charges, you have some region and you have charges qi at Ri with velocities ui, right? So there are a bunch of charges. Say I goes from 1 to n. Okay, and this is the system size is some scale of the emitting body given by L. And we are assuming that the time of variation of the charges, right? So this is sort of like the, time of motion, time scale for motion of particles. It's sort of like a frequency, inverse frequency is much bigger than L by C. So then the light crossing time. What does it mean? So if it is frequency, so this becomes C by frequency. So basically it means that lambda is much bigger than the length. So you're looking at wavelengths, right? This will just give you C by omega. C by omega is nothing but lambda, which is wavelength. So we're looking at wavelengths much bigger than the size of the emitting region. So long wavelength relative to size. Lambda is still much less than R, of course. This is just the extent of the radiation region. Okay. So, there are these, and you are actually looking from somewhere very far away. Okay, so what happens? What about this case? Right, so your electric field is again given by, the electric field due to a single charge is again given by this expression, right? Except that we have to add up the electric field due to all the charges. So this would be Qi R squared, R C squared, not R squared. RC squared. See, in principle, capital R depends on which charge you are looking at. But if the region is very, very compact, so L is much less than R, in that case, R is almost constant, right? There's not much difference between distance from here or here or here, right? Because you're very far away. So this R is almost, it's almost the same as capital R. N hat, for the same reason, is almost the same for all the charges. But the velocity or acceleration is not. So you have to sum over all these guys, right? In this regime where we are considering compact emitters, all these are constants. So they can actually come out of this summation. And what you have is n hat cross n hat cross qi ui dot this divided by r c squared. Right? Does this remind you of something?
Dipole moment.
Yes, it's related to dipole moment, because this is like summation qi acceleration of individual charges. So so this is actually called dipole approximation. So let's see. So this is nothing but d double dot, right? If we define our d, the dipole moment, as the dipole moment as summation of qi ri, right? So this is just the double derivative of that. Okay, so what about, so this is your electric field. What about the power? dp d omega is nothing but dw dt. Power is energy crossing per unit time. So this is equal to d double dot squared. I mean, we just have to square this sine squared theta. Again, this theta. So this is your dipole, the direction of the dipole acceleration of the system. Now, when you're looking at some angle theta, so this is, it's almost the same as what you had previously, divided by pi c cube. See, basically d double dot is nothing but qa squared. So d double dot squared is q squared a squared. So dp d omega, which is this, has, this has almost the same formula, right? Except that q u dot is d double dot now. Okay, this is fine. And again, everything sort of applies. What you have done is qa is replaced by d double dot, right, in the single particle formula. Now,
so there is r square in denominator.
There is r squared. Just a second. So this is power per unit solid angle. So no, there is no, right? This is not flux. This is power, power per unit solid angle. So if you are at small distance or far away distance, the total solid angle is still 4 pi. So it's this thing, right? So there is no r square. There is an r square in the flux, the Poynting flux, but not in power, or power per unit solid angle. Okay, so this is fine. Now, see, if we had made this approximation, where did this help us? Where did it go when we were sort of doing all this? It went in the fact that, right, so the electric field is, just a sec, given by this, right? And basically you also have, you have, this particle and this particle, this particle, right? So the retarded time, right? The retarded time is different for each of these particles, okay? And because of that, see, you have to calculate this expression at the retarded time of each of the particles, right? And they will have slightly different retarded time, right? And so when we do this, we are assuming that T retarded is the same for all particles, right? Do you see this? When we are sort of summing this up, we are not worrying about the difference between retarded time of this particle, because they will be different, right? If a particle is nearby, it will be, its acceleration should be evaluated at a slightly earlier time, and the particle which is far away, its acceleration should be evaluated at slightly, even more earlier time, right? But we are assuming that the wavelength is much bigger than the size, so so delta T retarded between these particles, right, is of order L by C, right? If L is the system size, and we are saying that this is much less than tau, the time scale for oscillation of the particles. So basically what we are saying is that all fields, right, fields due to all these points add in phase, right? Because we are not considering like interference type effects, right? In principle, this particle and this particle, if the phase difference between this point and this point is lambda by 2, they can destructively interfere, right? So here we are actually making this assumption that fields add in phase, and that is justified if your lambda is big compared to the size. So over the wavelength of your light, right, the path differences are actually much small, so they are almost adding, they are all adding in phase. Is this clear? Right, the phase difference between this point and this point is tiny because of this retardation is tiny, but this is not true in general. Okay, good. So this was right. So we can actually, just last thing, I have to create some space here. Okay, so this was in real space. So we can actually, this Fourier thing is always going to be there. So you can actually write dt. This is the dipole moment, summation qi xi is equal to, right? What is this? This is just the Fourier transform e to the minus I omega t d hat omega. So we are suppressing the vectors here, but D is assumed to be a vector. Right, this is the definition of dipole moment in time. This is the definition in frequency space. So D double dot, that's what we have. So I'm actually suppressing the vector nature here. So this is nothing but minus infinity to infinity. So d dt just pulls out minus I omega. So minus I omega squared, right? This is equal to minus omega squared. So that's what you have, omega squared, d hat omega d omega, and minus e to the minus I omega t, right? This is clear? I have just done a double derivative and that just pulls out minus omega squared. So this is your d double dot. What about e omega, the frequency dependence of electric field? This is nothing but, what I'm actually doing is just taking a Fourier transform of this, right? This is as a function of time, space and time. But if I take the Fourier transform, inverse Fourier transform of this, basically go from et to e hat omega, that's nothing but 1 by 2 pi, right? This is e to the I omega t e t dt, right? This is the electric field, and you can actually see that this is equal to minus 1 by c squared r omega squared d hat omega sine theta. I mean, this is just seen from this, right? If you take a Fourier transform of this, n hat r c squared, they just come out. All you get is the Fourier transform of this, which is nothing but d hat omega squared d hat omega, right? So omega squared d hat omega sine theta 1 over r c squared. So this is your electric field. And what about power? Power is dw by d omega d omega. So this is like a frequency distribution of your energy. That's nothing but squared of this. So this was just c e omega squared. This is equal to omega 4 by c cube d hat omega squared sine squared theta. So this is the frequency and angular distribution of power due to dipole radiation. Right, and we can actually integrate, so dw by d omega, again we can actually integrate over the solid angle, and what that does is it makes it 8 pi by 3 omega 4 by c cube d hat omega square. So you see the spectrum is proportional to omega to the 4, right? So what it means is that if you have this wave, this frequency of the radiation, which is produced by oscillation of these dipoles at frequency omega, it goes like omega to the power of 4. So this is dipole radiation formula for non-relativistic particles. So does it sort of remind you of something, this omega to the 4 dependence?
Rayleigh scattering.
Yes, Rayleigh scattering. Because in Rayleigh scattering, you can actually think of molecules as oscillators with some frequency omega, And if you have sunlight, for example, exciting those oscillators at that frequency, they can actually radiate much more at higher frequencies than the low frequencies. Good. So today's class, so this is what we have done. We'll start from the next time. So just look up the book and try to catch up. So just last thing. So if you make like a oops. So if you make a distribution of this power, this sine squared theta, right? So if this is the direction of your acceleration or of your dipole, so and this angle is theta, so it has a radiation pattern which looks like this. So that, basically, if this angle is theta, what this is drawing is how much power at a given angle. So if in this angles you have 0, at this angle you have something else, you have maximum power here, which is this is just sine squared theta radiation pattern. Okay, so this is this is drawn sometimes. So this is just a locus of this as a function of angle theta. This is just sine squared theta. Okay, so I'm actually going to end, stop recording. Any final questions? If not, then let me, where did it go? Okay, so then I'll stop sharing and I'll stop recording. Okay,